Okay, so let's get going. All right, so we were sort of in the middle of analyzing this, or looking over this, discussing this results of Christodoulou, and most of which I'm just going to assert, the real hard parts of the argument. I'm just going to make just some assertions, but still, it's sort of do some level of detail that I think will be useful. So remember, so what we had done is that we had reduced the system. So we had, okay, so maybe I'll just recall the original coordinates. So originally we thought of our space-time in these null coordinates. So we had these null coordinates. Then we introduced, in order to take advantage of self-similarity, we introduced these coordinates, which we called u tilde z. So u tilde was just equal to u, and z was equal to v over minus u. And remember, you have this picture. So at the origin, um, that's where we expect that's where the singularity, because of how the self-similarity works. So coming down here, we have our axis here. So here, this hypersurface, if it were to exist, would be u equals 0. Then we have the past of this thing would correspond to v equals 0. And then we introduce, so with self-similarity, it's very natural to write things as some, so at least in the region, so we do this in the region where u is less than 0, so that is fine to divide by u. And then using self-similarity, you could write all of the unknown, using their scaling relations, you can write them as some sort of power of u tilde, which I often call the scaling weight, times of a function which depends on this scale invariant variable v over u. And then we had this notation that we would do the math ring, little circle on top to denote the function of z, right? Okay. And so we had all those things, and what we had done was we had reduced, so we had these variables. Again, it's, well, not really that important. These are, well, somewhat, actually, somewhat important. All right, so we had defined um, uh, these, there are these variables discovered by Christodoulou. Um, well, I guess I can write this as, this is, well, yeah, d by dz. Um, so we have these variables, and and then we also had there was an s variable, s, a new coordinate s, which just has to be defined so that ds dz is equal to 1 over z phi of z. So this, you can use this to define, you can integrate this from different places, and then you'll be able to define an s variable, um, you know, in any region, in any region where, so in principle, this would work any region where this quantity, it has a constant sign, has a constant, has a constant sign. So in particular, using so remember the axis, this axis here corresponds to z equals -1. We sort of, in a way, that's a sort of gauge choice. We picked our coordinates so that um, starting here, u and v were equal like they are in Minkowski space. And the boundary conditions were such that, so for z, so if we had this ODE system, and assuming, that there's some kind of appropriate local existence uh, for that system near z equals -1, which is, of course, there's some degenerating factor. So it's not quite a totally normal ODE local existence, but something like that is still fine. I won't really, we won't discuss that in detail. But assuming there's some kind of local existence there, we know by the boundary conditions that, because yeah, you can see here, because R this fun R is always has to be positive, so it'll become positive off the axis. This is new, remember, is du of R. That's going to be negative, and much and like O of 1, so much bigger than R if R is close to 0. So this quantity will certainly be negative if, just by continuity if you move a little bit. And so and Z uh is negative 2, so this thing will not be 0, if you just move a little bit off the axis. Of course, some places where it has something, well, Z equals 0, which corresponds. So remember, so here, this is Z equals 0. That's, of course, will be a funny point for this coordinate. Okay, but and then in this coordinate system, sort of where it makes sense, you end up with this ODE system, which is then the bulk, where the bulk of the analysis sort of takes place. Right. Okay, so that was where we ended last time. So any questions before we keep going? Nothing on Zoom. Okay, so cool. All right, so yeah, so it turns out, and I mean another thing maybe that I can just remind you that we had discussed all these, there were all these boundary conditions. So all the boundary conditions, sort of boundary conditions are you know near z equals -1 or are fixed as of now. So we sort of, again, I did it at, some half level of detail, but I sort of was, there are all these unknowns, and just by the requirements that like things be reasonable at the axis, that we have a regular solution in reality, like our space-time is actually smooth in the axis after introducing some kind of Cartesian coordinates or something. That fix all these things. And even the scalar field, remember from the ODE for the scalar field, the only way that like the value of the scalar field had to take a specific like k, I forget, k over 2 or something. It was sort of fixed at the axis because that was the only way that that ODE could have a reasonable solution because there was some division by R, so something had to be 0 or else it wouldn't work out. Okay, so all the things were fixed. All right, so then now we can look at this system. Yeah, and so one thing that you see, because all right, so near z equals -1, so psi of course vanishes. So psi vanishes. Psi will vanish at at z equals at z equals uh z equals -1. And so why is zero? Yeah.
Zero equals u. Like z equals -1 is when b equals u.
Yeah. So you're saying, yeah, that it is the, yeah, sorry, I was thinking about something else, not about that assertion. Yeah. It's just the maybe this is just how you write that integral. Yeah. Okay. So then the claim is, again, and I won't, so the claim is that if you think about the S variable, so like Z, so if you look, so we're interested in a solution, let's say, you have some local existence, then you solve as far as you can do. So if you have Z in, some range, like -1 up to ZF, then this will correspond to s in well because you're ending up because well there's some like logarithmic divergence in the s variable as I mean you're going to be dividing by zero as you approach the axis. So it ends up if you if you think about it, then it sort of the range corresponds to, so -1 will correspond to infinity and then up to, well, whatever, whatever this value is. Okay. Yeah. It just becomes autonomous. No, it had Z. There was Z in it before we just got rid of there was a Z in the ODE. The first ODE for psi and theta. I mean, it's yeah. I don't know. I mean, probably you can also analyze that other system, but it's nice if it's autonomous. Yeah. Okay. So, all right. So then, all right. So then, okay, then you have to think about the conditions. So in some sense, so there's a critical point associated to this autonomous system. So there's a psi theta equals 0, 0, right? That's, if you if 0, 0 is just like as a solution to that. And so what now with the boundary conditions, so now we sort of push this -1 off to infinity. And now for our autonomous system, so basically what we want is so our the boundary conditions at z equals -1 now become the requirement, that our solution sort of emerges from this critical point, right? Now become the requirement that phi theta emerge from, I just mean like you do when you do this phase plane analysis in an ODE course, right? You have some subcritical point here, different local behaviors are possible, and you want the solution, which you want something which is sort of coming out of that, right? So when you run time backwards, it's going to it. All right. So then, okay. So now sort of what the beginning of Christodoulou, well, I don't know if it's the beginning, but the first part of the analysis of this, so Christodoulou undertakes does a systematic like local analysis near 0, 0 for this system, doing the usual things you do when you do OD, looking at linearization, et cetera, find negative eigenvalues, positive, depending on K, blah, 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 blah. But we'll just give sort of the upshot. So basically, what's interesting is he does much more than just find the solutions I'm going to talk about because he considers lots of different values of k. But I'm going to focus on the solution which is relevant for looking at naked singularities, and this turns out that k squared is between 0 and 1/3. All right, which is and if you want, you can even you won't lose much if you just think that k is something very small. Yeah. So we're going to, you can. All right. It's interesting is that he has there's a sharp threshold actually. Um, okay. So then what he proves is the following. And again, this reformulation of what Christodoulou did into some of this is being translated into these UV coordinates. I'm taking this from this appendix from this paper of J Deep. So if you want to look at the full things uh, anyway, that's just a reference for this part of the lectures. All right. So what Christodoulou showed is that there exists some S star less than infinity and a unique solution with satisfying the correct boundary condition sort of as S go to minus infinity, so that the following happen. So that, I guess I can say here, so that one, so psi of S is less than infinity. So I mean psi of S less than 0, sorry. And theta of S is always positive. Um, all right, so you can also yeah, and then sort of what's particularly interesting is what happens as we approach this final point. Um, yeah, so psi of s um blows goes to minus infinity as s approaches s this s star. So I guess so from the left. Um, theta of s approaches 1 over k as s goes to s star from the left. All right, and then other things. I'll just go here now. These are the yeah visible boards. All right, three. So to theta, so for s in so away from here, they are smooth functions. Right. And yeah, so then you can do, and you can in fact, yeah, so this is sort of what's you kind of prove first. And then again, well, so I mean, yeah, so what's the way to sort of say this? Well, all right, so this sort of corresponds to, it's like a little, so in a way, like, I mean, you can look into the system and in a sense, theta equals, well, obviously, so if, yeah, theta equals 1 over k, well, yeah, maybe it's not quite super straightforward. Um, I guess, I mean, so here, as you approach this point where this is going to minus infinity, of course, uh, the s coordinate is not necessarily the best coordinate to be looking at. You can sort of introduce, so what Christodoulou does to analyze what's happening there, he introduces some other coordinate where, again, you can get some other ODE system where now the picture near s equals s star, you can do some local analysis near that point. And again, linearize, look at blah, 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 look at these things. And what's the upshot of all of that is what I'm going to tell you. It's just that these are ODEs, and so there's a lot of rigidity and like possible behaviors. Uh, okay, so what is able to show is that you have that 1 over psi of s equals 1 minus k squared times s minus s star plus big O of s minus s star squared. And all right, so it's not just that psi of s is diverging, so you get some very precise, the way that it's diverging. And then this is not just equal to 1 over k. I mean, you actually there's some constant depending on k, and then this is sort of coupled there, and then you get something which is big O of s to there's this numerology which shows up. All right, you can do that. And then once you've determined the asymptotic, like the explicit, this kind of refined asymptotics of these variables as you approach this final point, we can also go back to the z coordinate and translate and relate z with s. And yeah, so here's sort of a final thing. You can get that s. Well, this is really not Christodoulou. This is J Deep's appendix. Because Christodoulou never worked with this like u tilde z coordinates. Um, so what you get is this is basically well equal to there's some constant times little o of 1 as z goes to 0 times z to the 1 minus k squared. So basically, so I mean, in particular, so as s goes to s star, you have the z. So z is going to 0. So which corresponds to approaching that past light cone. All right. So now picture up there. So here's our origin. This is where we started. And then we had this this v equals 0, which is the same as z equals 0. So the solution that we found there, where we use this s coordinate because it was a nicer OD, when you translate back into the z coordinate, it corresponds to a solution here, right? And we understand, because of point 4, we understand very precisely what these unknowns are doing as we approach there. All right, and again, there's a lot of stuff hiding here. Um, but you can think, okay, there's something about, what goes into it. Again, it's you sort of look at the different critical points of this system and you prove, under different regimes of K, you kind of track where it can possibly go. It's this kind of arguments. All right, and then once you know that you're going to a certain critical point, there's a lot of rigidity. There's only, based on just a local analysis near that critical point, you can understand the like unstable, stable manifolds and figure things out. And that's where this kind of very explicit stuff comes from. Yeah. Um, yeah, because some things vanish. Yeah, it's not, well, in this proposition, 1/3 is not relevant actually yet. I think actually it's one is actually, it's funny that you say that. You can look in the paper. Yeah, it's actually for a later stage. So what you can think is, maybe getting ever so slightly ahead of myself. They're kind of two, uh, they're two sort of moments. There's kind of like, you can think, well, in terms of the autonomous system, and maybe, well, yeah, I'll just say, speaking very vaguely, sort of the axis sort of corresponds to one critical point, which is the 0, 0. And then this v equals 0, there's kind of a solution which corresponds to, if you get to that critical point, it sort of corresponds to a v equals 0, which is in the past of a singularity. And that's kind of, in some sense, this is that critical point. You can't work with, maybe you have to switch variables to something which is, there's another variable they sometimes works with, which is 1 over psi. And then in that system, what happened is you connected that critical point to another critical point, which corresponds to that one. And then you have to go, but then you also want to connect it to something which is sort of, well, can eventually be made sort of asymptotically flat, because you want to have good asymptotics at spatial infinity. And that's another critical point. And so the k to 1/3, so the ability to connect the axis to sort of a v equals 0 that looks like you want it to look like, that already, if k is too big, you don't hit that critical, you won't hit that. And I think, if I remember, you can just look at the paper, but it's very explicit in the paper. I think it's 1 actually. So if k is bigger than 1, you go to some other critical point, and which doesn't correspond to this picture. So then if k is less than 1, you're there. But then we're going to sort of shoot off from v equals 0, and again there'll be a constraint on k, and that's where you'll need, k has to be smaller than 1/3 in order to uh, in order to have sort of the r equals infinity geometry look like you want. In this k, well, we'll see in a second that k is, what values of k you can do is extremely interesting, because it has a lot to do with the regularity of what you find, which is exactly what I'm going to say next. But maybe, are there any other questions before I do that? No? All right. So, okay. Well, again, this is going to basically be an assertion, but so you can, okay, so because we have this and we have this, in reality, you can get, in fact, you have full asymptotic expansion to all orders, because again, it's this ODE. So you can now, you can relate, remember, these things contain all the system of all, I mean, these contain the information of the full system, right? I asserted that too. So if you sort of do all that work, translating everything, what you find is that, so all of this eventually implies something kind of interesting. Okay, so we can translate everything back to the original unknowns. Translate everything back to the original unknowns. So this is at this point, so it's tedious but algorithmic, given once you have this information. And what you find is that sort of, so as z goes to 0, you find the following thing. So, all right, so your so the r variable, is reasonable, sort of, it's kind of bounded. This lambda, so remember that lambda is d v dr, right? And remember, so R has scaling weight 1, so dV of R has scaling weight 0. So for the self-similar solution, lambda is actually just equal to lambda of z, right? So this is dV of R in these coordinates. What you find is that this thing, when you translate it, as you go to v equals 0, is blowing up at this rate. You find that remember nu correspond is dr du. That one's not doing anything weird. The scalar field, well, I'll say the scalar field is bounded as you're going to z equals 0, so that's fine. But this dz of the scalar field, that's the sort of the non-trivial derivative, that's also blowing up, and also at this rate. Okay. Yeah, and you can also look at higher derivatives. That's maybe not too important right now. You can look at the lapse. So it turns out the lapse is also blowing up at this rate. All right. So you see this k is intimately related to the regularity of these things as you go to b equals 0. And then there's some other things that are also true that so this is more for regularity purposes. And then what's maybe interesting is you can also look at this. So remember there was this mu, which is this mu function, which is this ratio of the two is there, just it's convenient, some formulas. But this is what this is this is the Hawking mass, remember, which is a natural like sort of notion of energy in the problem. And then you divide by r. When you divide by r, then this thing has scaling degree 0. So it's kind of some scale invariant notion of energy. You can look at this on v equals 0, and this turns out to be equal to k squared over 1 plus k squared. All right. So that one's less, I bring up that one is less about regularity, but to contrast with, so in the scale invariant setting, remember those ones on v equals 0 had vanishing Hawking mass. That was related to why they ended up being trivial to the like, I mean, this region, the previous solutions we did, they were flat here, right? And that was related to the fact that the mass was 0 here. These ones exactly see that when you turn on k, that becomes non-zero. And well, these solutions are not flat in there. Okay, but this stuff looks kind of weird. So let's think about the implications of that, unless there are questions. No. Okay. So now we need to pause, maybe sort of step back from this ODE analysis and think about what what's the significance of the space-time we're trying to construct. What are we hoping will be the significance? Well, what we're hoping is for an example of evolution of we're interested in trying to find examples of naked singularities, right? But not just that we want a naked singularity, we want one that arises from the evolution of regular data. Remember, I made this point that you don't want to have a bad single. I mean, they could be interesting for other purposes, but for us, we don't want there to be a singularity already in the data. That's less interesting to us. We're interested in those forms. Okay. So with that in mind, what's the relevance of that? Well, that's what I'm about to say. This will look like not nice data. Well, not, and again, it's subjective what nice data is, but what's sort of less subjective, but still subjective, is that it should get worse, right? Whatever you start with, if it's going to be you start with something that should be in some kind of class where you have well-posedness. That seems reasonable, and then it should get worse. All right, okay, that seems fine. You can still debate lots of things. All right, and okay, so what's the deal with this? The problem with this is, I mean, this data is just nasty, right? I mean, right, this looks like not even BV. All right, because well, I mean this or maybe is it? Yeah, but I mean, but this is like the very geometry is not like, for example, this lapse is not even this thing. This is like the metric is not even defined in a C0 sense. For example, that's pretty bad. Okay, but well, we don't panic. We, you know, we know this is we're studying geometric PD, right? So you always remember, right? Schwarzschild also looks singular at r equals 2m. Maybe you could do something. And it's a little suspicious. So if you look at these blowups, right? It's the things that sort of involve. So this, okay, we've written in the self-similar thing, but this was a u derivative. That was fine. This was a v derivative. You get this blow up like this. This dz. Remember, all derivatives basically, well, I mean, you might think this is some combination of u and v derivatives when you write it out, but there's a v derivative there, a similar blow up there. It's also the same blow up there. And if you then think about what the metric looks like, it leads you to the following. Um, the following idea. So this is now it leads to something very important. So key idea, you can introduce rescaled null coordinates. So rescaled null coordinates, which are the thought, which, oh, and here, unfortunately, I think I kind of use the opposite notation of JD. He calls these U and V's and the other ones UV. So apologies. But I'm very used to the other way of doing it in other work I've done. So I did it like this. All right. So yeah, so this is all, so we're all, this is all, let's say for now in this region, in the region where we have the solution. So V is negative. So, all right, so put absolute value to make it positive, then raise it to this 1 minus k squared. Right, and then, so one thing, I mean, you can go ahead and notice, right? So first of all, so we have, so here is the, right, this is the not sort of the not spherically symmetric part of the metric, right? So, you know, so D from this formula, right, we see that, of course, this will be, I'm going to write it like this. It's very easy to make a minus sign mistake. So dv will be, right, so you're going to get 1 minus k squared times this to the minus k squared dv, right? And so, right, and so you can work this backwards. So dv is equal to minus v to the k squared times 1 minus k squared minus 1 dv check, right? Okay. But then on the other hand, so this z, so z here is, remember, is u over minus v. So z to the minus k squared is going to be, well, let's write it like this, like u to the minus k squared times, times, well, v is negative here, yeah, so, well, this whole thing is positive, yeah, so let's write it like, like this, to the minus, wait, that can't be right. No, sorry. Um, oh my God, this is V over U. Right. Makes sense. Okay. I don't know why I wrote that. Yeah, so okay, that makes more sense. So then it's like this, like it should be. All right, remember, well, I was saying the right things before. I said the laps was blowing up. Yeah, so the point is V over U. So this, so you see, so from this thing, the lapse is blowing up. So you have this function of U. Remember that in this region that we're in, maybe I'll just draw the picture again. Here's our axis. So here's v equals 0. So this whole region, so here's say u equals 0. I mean, we don't know if we're going to even get there. But in this region, u is less than 0. So like, you know, and so again, like I said, it's about, we're thinking about like initial data. How reasonable is our initial data? So let's consider as initial data, let's draw some hypersurface down here and imagine that we start here and we solve up. And what we want is the data here to be reasonable. So the point is the data here I could take to be, say, u equals -1, right? U is not, the point is we're not afraid of u going to 0 here, right? In the data, the issue is only v. And, right, but, all right, so this u factor, well, it's not blowing up anyway, but it's not really. Of course, you don't want the lapse to go to 0 at a regular point, but u is like -1 for the at the data. But this is a problem because v is going to 0. But this factor exactly compensates. So this thing will just be equal to minus omega squared times, again, we could just write this absolute value of v to the k squared times du. Well, u is just the same. Becomes this, right? And then this function now has a regular limit. Right? So this cures that, for example, that blow up of the lapse. But it does more. So that sort of deal, at least to like the pointwise behavior of this function, that's dealt with. But it turns out that it also, you know, um, is exactly the change of variables is exactly what solves these, because you just do the right. So you just want to check, so d by dv, so d by dv will be equal to d check. So how did I define it? If v, okay, yeah, times, right, dv check, dv hat, I don't want to say check, dv hat dv, all right, so we do that, and then you're going to get 1 minus k squared times minus v to the minus k squared times d times this, right? And so again, so once you move that back over here, you now see that, for example, so lambda, I wrote there as dv dr, but now we see that d, so I don't know, you can introduce some other notation like lambda hat check, or let's just write it like this. So this says dr with respect to dv hat, this will now be fine as this is here. All right. Okay, so that's this first sort of important observation. And then, okay, but now you might be getting a little confused because you say, well, why is there like is there a downside to this? Like why, how were we not in this situation before? So I mean, because this is still a double null coordinate system, and I thought we were working in general double null coordinate system. Well, we weren't quite, because there was an extra assumption. There was an extra assumption, which I didn't remind you of today. So the point of the original, so in the original UV null coordinates, it wasn't just that we were working in null coordinates. We were working in null coordinates where, so here, the self-similar vector field, which I think Christodoulou calls S, was given by the usual formula, U du plus V dV, right? The point is, in these hat coordinates, that vector field is not going to look the same. So we're just sort of deforming, it doesn't have the same formula in those coordinates. All right. And if you work it out, so so this turns out to be the same as u hat du hat, and you pick up sort of this deformation here. Right? So this is the key point. So I was trying to emphasize this before, that when we work, when we're setting up, even back when we did the scale invariant solutions, I said we're going to assume that we have a double null coordinate system, and then we have to say in these, we have self-similarity. The most abstract version of self-similarity just says there's some one parameter group of transformations that does something, but we want to solve it. We have to make some choices, what that looks like to solve the equations. And I'm saying the naive choice is to assume it's like this, but that's a choice. Like that's not, you could also pick coordinates where your self-similar field looks like something else. And in this case, it really makes a difference. So it's in these coordinates, you have better regularity across across v equals 0. Now, how regular are you? It's a very interesting question, very important. So one thing you can see is there are these kind of things, which, so it's one thing. Yeah, and again, I'm not going to do any real computations here, but I'll just say there's some full expansion here, and there's some weird algebra of K showing up. And what would be really great is if, you know, you do this coordinate change that makes some things work. But okay, that's like that makes the first derivatives of things work. But we also we want more things. But there's this weird extra stuff going on here. We can't, we sort of used up our rescaling freedom because, the other natural rescaling freedom to keep you in double nulls to do something in the U direction. But um, but that doesn't but that won't affect anything in the across v equals 0 because you can rescale u by a function of u. So you're sort of stuck. So this dealt with the first derivatives, and it turns out that, well, at least for the values of k that end up working for the solutions, we're not going to be able to get a C2 solution. All right, and in general, what you get is that so in general, this yeah, so what you conclude is okay, so in this these coordinates, sort of all quantities extend in a C1 fashion, extend in a C1 fashion to v equals 0. And in general, what you just have is that dv of the scalar field will be Holder continuous. Will be Holder continuous at v equals 0, and the exponent with actually, I don't know if I wrote down the formula for the did I? Oh no, I didn't. That's annoying. All right, yeah, I didn't. I forgot to write down there's an exponent with um with its Holder exponent. Well, let's, already to keep things simple, let's just imagine k is very small. With Holder exponent, which is sort of like a, you know, big O of, well, I'll just say it's kind of like it's certainly like k squared as k goes to 0. All right, so once you remember k equals 0 just corresponds to you can see when k equals 0, then there's no coordinate change. It's actually that those first set of solutions we discussed where everything's flat, right? Those ones, you then had this issue that right, then this thing was 0, so all that stuff was flat. So you turn on k a little bit, you sort of break that rigidity, you get something non-flat, um, and you also sort of improve the regularity like a bit, even with a little bit of k. So before, remember for the scale invariant solutions, the derivative of the scalar field is the most important quantity here always, right? The derivative of the scalar field jumped. That was what happened for the scale invariant ones. So now the derivative of the scalar field becomes Holder continuous. All right, so you've increased the regularity. All right, and so in particular, the data is better than BV. All right, you can check this. So remember, Christodoulou, has this well-posedness thing and the so-called solutions of BV. Remember, it's a little confusing. BV it's not that the scalar field's BV, derivatives of the scalar field are BV. Anyway, so this is better. Even once you turn on a little bit of K, it's already better than that. So it's better than that class. But the singularity, you can kind of see that the singularity will actually force you to leave B. But and you can already see that from different ways, but sort of the origin, cannot, be in the space-time and be BV. There are different ways to see that. One of the ways from the Hawking mass, so we know that one of the requirements, if you're going to be BV, you need that this ratio mu has to go to 0 as you approach the axis. So as you approach this along any null hypersurface, along u equals constant or v equals constant. All right, but you see, mu is not for the self-similar one. Mu is just like this thing is scale invariant. So mu is so for our solutions, mu really is just the function. It's just this function of v over minus u. So along v equals 0, it's a constant, and this constant is non-zero once you turn on k. So that's one thing. Um, that's maybe and then another you can also see I guess it's not uh yeah, you can also it's not maybe clear yet from what I've said, but another thing, maybe more a more or maybe you don't like the hockey mask, whatever, but you can also see is that what you can check is that so along v equals zero, remember, so in this case, so if k, so when k is not zero, then du of the scalar field, so this so scalar field has weight zero, so one derivative is minus one. So this, has to be of the form minus, um, u tilde times some function, right, of v over u. And so, and then so at v equals zero, so at v equals zero, you just get this thing at zero. And again, in this context, when k is not equal to zero, this will not vanish. All right. So again, this was this thing that in the first class of solutions we did, the scalar field was constant along these null hypersurfaces. So this derivative was zero. And so this case is not zero. And then so in particular, there are these scale invariant these norms. So this integral along v equals zero, there's this norm that shows up in the BV theory. This thing will be infinite. And remember, this is also, I also pointed out before, this is something which is scale invariant. So if you rescale the u coordinate, whether keep the double null form, but rescale it by a function of u, this integral stays the same, right? Because of how the change of variables works. So this is, you should think this is kind of a geometric statement. You're just saying along, then this thing is infinity. So this is a nasty singularity in the derivative, even though originally our derivative is Holder continuous. Okay, so that's, we still haven't, you know, we've still only done the solution here, right? So we don't know. I mean, naked singularity is also supposed to be asymptotically flat. There's all that other stuff. We haven't got to that yet. But at least so far, things check out. And this has, all right, and it's still okay. The C1 alpha, maybe be nice to do something even C2, but fine. But still, it's regular enough that we can argue that this corresponds to sort of a singularity um, singularity formation. Is that so that maybe I'll ask questions and then that'd be a natural place to take a break. Any questions? Yeah.
I understand that all the quantities now extend in the C1 version, but on the other hand, our coordinates itself are not C1 anymore, right? At b equals zero.
Yeah, but that doesn't remember, we're just coming up with the space-time, so we don't need to work in those UV coordinates. So it's like in Schwarzschild where, yeah, this is sort of a point. This is a funny point of confusion, actually. People talk about Schwarzschild, they sort of talk about it incorrectly. So people will look at this metric, this Schwarzschild, right? And then you say, well, R equals 2m looks like, this is what people say, looks like a singularity, but actually it's a removable singularity. It's not quite correct. Because in reality, you should fix a differentiable structure. So I mean, if you say that my manifold really is TR, and the TR in the sphere up to 2m, then I mean, this is a singularity. I mean, the point is that you say that it's a removable singularity is because I say that no, there's actually my manifold is, you know, yeah. So what I'm saying is, so if you say that my manifold is, TR theta phi and say this, and yeah, let's say I try to include, I try to include this. I can start with this as my differentiable manifold. I can put this metric on it. Then this is not a removable singularity because this is supposed to be a smooth coordinate. It's like you said, if I do a change, then I'm changing the thing. But that's not, when people say it, they don't mean that. What they mean is that, no, what I do is I say, no, I only use this differentiable structure away. And then when I introduce some other coordinates, whatever they are, and Schwarzschild is V, whatever, it's not important, I'm introducing another, so anyway, so it's the same thing here. So it's true, we started drawing this picture in these UVs and whatever, but we're just coming up with the space-time. So yeah, it turns out that this afterwards, actually this V coordinate is the singular one, and the V hat is the one I should have sort of started with at the beginning. And it's just that, so this kind of thing will happen. Um, uh, well, if we get to it at the end of the course, even with the vacuum analogs of these. And there's kind of there's always this back and forth that you'll say, why did we even work with the V coordinates? I mean, one of the points is that in these UV coordinates, even though they're not regular somewhere, I mean, these are algebraically the nicest because things look normal, like they look like usual self-similarity. And so it's useful, even though it turns out that it's not actually what defines our manifold. Though again, away from maybe some few bad points, they are like away. So in the past here, it's fine. Right? Does that answer your question?
Yeah.
Yeah. Other question? Why? Where was k squared minus 1/3 used? So this was asked earlier. So it's actually not, I mean, at the level of detail I'm going to present things out, you won't see it. And it's actually not used yet for what I've done. It's when you construct the outside part of the solution is where the k squared minus 1/3 ends up being relevant. But again, I won't be clear from the level of presentation I do. All right, so, okay, so it's, let's take our 10-minute break, I guess. So let's reconvene at 4:12. Let's keep going wherever we were. Okay, so now the next step is to do the exterior. And again, I'm going to just sort of assert a statement from Christodoulou. So now, so remember we had this, so you can work, it's sort of funny. So we had this S coordinate, which, remember to D, which was like this, right? So this S coordinate, you can't use it near Z equals 0, and that, which ended up corresponding to, uh, you know, these bad regions. Um, well, it actually sort of, well, because this goes to infinity. I mean, the S ends up being finite, but this ends up being a funny, remember, so originally we had S sort of up to here, right? And yeah, I'll just say like the possibly something funny happens as equals 0. And we saw that, well, indeed, there was this in the original coordinates, we have to switch this V hat, or V hat, and blah, 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 blah. All right, but once, sort of forgetting about S infinity, you can then consider the region S bigger than S star. You can sort of, if you want to think in terms of Z, I mean, you can integrate this. So when Z is negative, you integrate this from you just pick your favorite value of Z that's less than 0 and integrate from there to define the S coordinate there. Then when we want to work in this region, assuming you have a solution defined in the Z variable, you can always just pick your favorite Z now greater than greater than 0, integrate from there, and that will define this again, as long as this thing doesn't vanish in the region where you do that. All right, and you can also invert that procedure. So again, so what Christodoulou does is he again is studying that ODE that I erased. I won't rewrite it because it's not too important. It will study that ODE, but now sort of in the region where S is bigger than S star. And so again, it's sort of in the analysis is what actually goes into his analysis is like I said for a suitable change of unknowns, this S equals S star corresponds to some critical point of the system. He linearizes, finds the eigenvalues, understands stable and stable manifolds of that, and then repackages that out to some kind of local existence near S star. And then he wants to understand for different values of K and the different solutions that come out of there. When do you go to some other critical points? Okay, and then that's a lot of work. I'm giving you some short version of that. I'll now give you a short version of one of the things he gets from that right now. So here's what is written as proposition. I don't know if JD called this. I feel like we should call this theorem. Go on. he worked hard for this, you know. All right. So yeah. So all right, so this now corresponds to the solution here. So one thing that's interesting in this region is that so if you remember at the axis, I made this point that there was no flexibility. There was just a unique of course everything depends on k, but imagine k is fixed, then there was just one up to like just fixing your coordinates, which is like a trivial degree of freedom. There was basically one solution, right? But now it turns out that when you cross S star, you now have another degree of freedom. And again, that should not be surprising or possibly not surprising because we've done all these warm-up problems slowly, and we've seen in all of these self-similar solutions that when you cross v equals 0, you get an extra degree of freedom. So in the wave equation case, that was where you were able to add an arbitrary jump of the derivative. In the scale invariant solutions, that's exactly, the metric was flat and then it became non-flat and you had a free constant over, that was unfortunately called K there too, but it's a different K. That was the one parameter thing of freedom here. So similarly here, there's going to be a one parameter, so you have the freedom to stick in a one parameter family and it will, still solve things. Okay, so all right, so you have a so for of course there's some, well here, okay, I'll say so for uh suitable choices of a constant b. All right. For suitable choices of this constant b, you'll have a solution which exists for s all the way up to s equals infinity, from s star to infinity. So you have a solution. So you have solutions psi and theta in that region, so that the following things hold. So so some of these are not that important. So psi always stays between 1 at infinity. Sounds weird. Didn't it go to minus infinity before? Maybe that's a typo. Oh no, wait, 1. Oh, but psi was going to 0. Oh, whenever psi. Okay, forget about that. And anyway, it doesn't really matter actually at the level we're doing it. I think I just wrote down the wrong thing. All right, one thing is, so what happens as s goes to infinity is that psi of s will converge to 1 and theta of s will converge to minus k. All right, so this one, again, okay, I erased that original ODE, but you can check that sort of this psi theta equals 1 minus k. This is a critical point of that original autonomous system. So, I mean, so what we're doing here is just this thing, you have critical points and we're finding orbits which are, we're connecting the critical points, right? That's a thing that's often of interest on ODE systems. All right, so we start with that critical point at the axis, 0, 0. We connect it to that one that corresponded to v equals 0. And then we're saying if I pick this constant, right, and in the proof of this, k squared less than 1/3 is used when you do this analysis, that you end up, the solution will drive itself to this critical point. All right, so yeah, so then let's also look sort of, all right, so as we approach S star from the right, so again, you might think, so before we had a pretty refined description of what happened as I approach S star from the left. You might think, well, why isn't it the same? Well, again, it's not, because we're not working with smooth solutions. There can be these, like with, so in the scale invariant solutions or for the wave equation, we had the derivative was jumping, and so there were difference in the limits. In this case, we're going to want to keep this sort of level. So our derivatives are not going to jump for the scalar field now because we want to keep this Holter regularity, but there will be some higher order thing which jumps. So the asymptotics are not the same. And this is where, and it's in this extra higher order term where, again, by analogy, you might guess, is exactly where this constant comes in. That's the sort of extra piece of data. All right, so okay, but you don't see it with this psi, because this looks like this one sort of just behaves the same as it did on the other side. So again, at the level of detail of this, not too important, I'll just say plus higher order terms. All right, so this is what it looked like on the other side of this. Where the freedom comes in is in theta. So remember theta, I don't know. Just remember that theta was z psi times this theta, the theta variable included the information about the derivative of the scalar field. Remember, the scalar field is what all the dynamics are actually included in the scalar field. So, so when I write that theta has some freedom to change, you should think of that as being completely analogous to before when the derivative of the scalar field did something different. What's interesting now is that well, like I said, that here it doesn't correspond to a jump in derivative anymore. That's because of this weird somehow this case self-similarity ended up leading us to change, forced us into this coordinate change, and then it sort of works. The freedom ends up manifesting in a different way. So okay, so to leading order, things are sort of fixed, and there's already something kind of well. Yeah, actually, I wrote this before, but I didn't. I should have said something about it. All right, so here's part of the solution. This is basically what was there before. So this is like what was there before it. So your solution looks leading order, like there's this 1 over k, and then so this 1 over psi, remember psi was going to infinity, so 1 over psi is going to 0. So this is all right, but there's some constant depending on your choice of k that the next order term is sort of fixed in the expansion. But something I forgot to mention before is that this is interesting, right? This is 1 over k. Remember, you don't lose much. Remember, I said by thinking about that k is, greater than 0 and very small. And it's interesting what you see here is that this is enormous, right? This is something which, if we get to it in the course, we do the vacuum equations, is something very interesting. Well, I mean, so here, sort of the way we're doing this, this critical point homogeneous system. I mean, solutions being large or not, or somehow like it's fine. I mean, you just understand critical points. You can do various arguments to try to connect things. But if you move to sort of PDE world, and especially PDE where your conserved quantities are not sort of so-called supercritical PDE, where you don't have great conserved quantities that control things, something being large data and needing to control it is scary in general. So this is right. So you should think like so this thing is not big, right? But this is huge, which is telling you that like the derivative of the scalar field. Right? I mean, we know the thing is Holder continuous, but it's massive. Its derivative is massive if k is small. Right? So that's kind of weird. All right. Somehow for this analysis, it doesn't pose any special difficulty the way Christodoulou is doing it. But all right, then the freedom shows up. So you have this constant b, and the next sort of the next term is something like s minus s star. This is sort of this weird. We sort of saw this on the other side, and then I'll say plus higher order terms. Yeah, so this is sort of a funny thing. So again, if well somehow if is this bigger than 1? When is this bigger than 1? So k squared is bigger than 1 minus k squared if k squared if k wait. That's a little confusing. Oh no, that's it's not bigger than 1. Yeah. Yeah, so this is what's sorry. So this term, so remember k squared is in 0, 1/3, right? All right, so here is the next term that shows up in the expansion. And so what you see is that, so it's funny, so this term in the expansion was sort of fixed, it turns out, when you do the ODE analysis, it has to be similar to this. This term is sort of free, but this term is lower order than this one, actually, because this one's going to 0, like s minus s star. This one has this k-dependent thing. And with the range of k that everything work out, this is lower order. But it is still, and so if there wasn't this, then there would be a hope that like this thing was smooth in S, for example. But because of this term, this is sort of why you get stuck with this Holder regularity. But again, this does go to 0. So you do get some Holder regularity, right? All right, so that's and you're sort of free. You have this is where the freedom ends up coming in. Okay, and again, before we had the freedom was to put in a jump of the derivative. And so why, I mean, you might be a little, think it intuitively, it's a little weird. Why is the freedom now sort of not, the freedom like got displaced? But it's kind of like our K self-similarity forced us to deform the coordinate systems in such a way, and then that sort of deforms where the degree of freedom came in. Again, if K is small, kind of the movement of this, so theta is at the level of derivative. So the movement of this from the constant level is sort of small. If K is very small, this is like barely going to zero. But it's like this slight increase in regularity when you turn on K. Right. And then, like I said, this is why it's then interesting to ask how big you can take K, because if you could take K so that this thing was one, that would be great, but you can't. So too bad. Yeah. So if you could get up to K squared equals 1/2, that would be really interesting, because then the swing would be one. But you can't. So all right. So that's the behavior as S goes to S star. And then you also want the behavior as S goes to infinity. And again, you're approaching this critical point. So you do the linear analysis around there. There's a lot of rigidity about what can happen. And so you're able to determine pretty precisely what's going on there. Um, right. And I mean, again, at this level of detail, it's really not that, I don't know, it doesn't have that much meaning, the things I'm going to write here. But, so psi, so as S goes to infinity, it will be like 1 plus there'll be some constant being 1 times e to the, um, you get some sort of, let's say, plus higher order terms. You have some asymptotics like this. This constants might depend on the choice of that constant. And then theta, all right, so the leading order, it's going to K, and then you get some, uh, something times this constant, times it's like, if K was 0, it would be a clean exponential fall off. The K sort of deforms the power a bit. Then there's plus some other term falls off like this, and then some higher order terms. So, okay, something like that. And you're also able to, you can also determine that sort of as that Z is essentially like e to the S as S goes to infinity. All right. Okay. So then the final thing, so we've constructed the solution in the biggest range, for all S. All right. So now, then what you have to do now is you have to remember how we were drawing this picture. So we have this gamma here. All right. We have this was V equals 0. So here is U equals 0. And what you can think is that um, so so having the solution from S going to infinity corresponds to, so we have the solution in this region with, of course, that we know that when Z equals 0, you have to introduce these Haddock coordinates, whatever. But forgetting about that, basically we have the solution in this whole range. So that corresponds to, for example, we know the solution along, so you can look at, say, U equals -1 and this thing going, all the way. So we have the solution here. And then I've made this point, quite a few times in these lectures that if you know on the whole such thing here, because of the scale invariance, the scale invariance is here. So once you know how everything behaves when you move along here. So if you've solved for the solution all the way to infinity here, that actually defines the solution in the entire region where U is less than. So we've defined a solution in this entire region. All right, in particular, again, it's maybe tedious, but now it's something algorithmic. Once you have these expansions, and again, in reality, you have these expansions, like the full asymptotic expansion. Once you have all these expansions, you can work out what they imply about the behavior as you go to U equals 0 by just, as you approach U equals 0, you're passing all these rays, and these rays just go further and further out. So these expansions as S go to infinity are equivalent to some expansions as U goes to 0. You just have to work it out with all and I'll just tell you. Well, I won't even really tell you, actually. Basically, what basically happens is something, so at U equals 0, there's a very similar behavior. It's a very similar story to to v equals 0. That is to say, things won't look C1 at u equals 0, but you can introduce a u hat coordinate that, well, maybe we have to give it a different name. I don't know. So there'll be, say, a u check coordinate where so v check will just equal v. And then this is now some rescaling of u, 1 minus some suitable, whatever. It's not that important. You'll do some rescaling of the u coordinate where then things will become, and then everything eventually you get that, d u check of phi is Holder continuous up to u equals 0. But of course, I don't mean I always mean like not including that point, right? So of course, away from 0, 0. All right. So that's kind of nice. So, all right, so how much time do I have? 4:32. Okay. All right, so let's think about what this picture looks like now. Oh, now I don't have to redraw I have the picture here. All right, so let's just think, schematically here. So we have, or maybe I should erase this. All right, so we have this picture. So we can even now, if we want, we can even bold that in because the solution it extends to u equals 0. The scale, let's say, the scalar field is the derivative is Holder continuous in the direction du of it. I guess I didn't say, so dv of it will extend smoothly to this, but the normal direction will be Holder. So what we have is, this is already kind of interesting solution from the point of view of, well, various of the cosmic censorship conjectures, not all of which I explained in the first weeks of the course. But one thing you see here is that you have, so there's already a singularity here, right? So we said this is like, you can call it like a BV singularity, right? Because remember I said this diverges. I mean, there's something more serious actually that I should have said earlier. Remember that we were always working with this thing, right? But the true scalar field has that logarithmic term. So I mean, of course, it's related to this being infinite. Is that of course this at v equals 0 has a is going to have some suitable constant times log of u. Or if you want to work in the regular coordinate, doesn't make a difference, right? So along v equals 0, this thing's blowing up logarithmically. So this is a bad singularity here at this point. But then then you have the future light cone of that point. And now all of a sudden, but so that's true. But if v is positive and u goes to 0, then even, well, right, then we can work in those coordinates. So we can approach, as long as we don't approach there, if we go a little bit over an approach, then this is even Holder continuous. All right, so this is an example of something called kind of is a Cauchy horizon. So this is CH Cauchy horizon. So what's happening is that you have a singularity, and once it's a singularity, you don't know what to do. You can't really solve past the light cone of that singularity. It doesn't make sense as a globally hyperbolic spacetime. Because if the way to think, because if you tried to go past it, what would, you're like missing data. You don't know what to put. You can't go uniquely. You can always put some extra data, say that way, and try to solve there. But there's no unique way to keep going. In fact, there are many non-unique ways to extend here as a solution, and that's kind of weird, right? So these things are considered sort of weird. So already that's weird, but all right, but not strictly speaking yet relevant to what I discussed as the the full weak cosmic censorship conjecture, which is about asymptotically flat data. So here's the question: is this spacetime we get that we obtained? Again, it's all defined now all the way. No, all the way. Is this spacetime, asymptotically flat in any reasonable sense? All right. In other words, does this really correspond to something coming from like localized initial data? Um, because again, you might think if somehow as I go out to infinity, I'm pumping in all this like weird stuff in the system, and then maybe it's like, for the heat equation, you have non-uniqueness when you allow really weird behavior at infinity, but no one thinks the heat equation is bad. That's just like you shouldn't put weird stuff at infinity, right? So you need to check like what's going on at r equals infinity here. Again, okay, there are lots of different, like I sort of briefly indicated in those, I think during the winter school, there are many different notions of asymptotic flatness depending on what you're after. For now, let's just keep it simple. So we're gonna, and there's also this question of, do you want to work with a null hypersurface? Do you want to work with a space-like one? Sort of more canonical to work with a space-like initial data, but let's just work with this. Let's just think of putting data, here and then solving the future of that and just ask, what are some requirements that should be true if this is going to be asymptotically flat? I'm just going to impose some very, very weak requirements. So we'll say, so here's some weak requirements. Well, so one, if that's the case, we should get the R function when I restrict it to u equals -1. I mean, this should certainly go to infinity as, v goes to infinity. I mean, it should look like, because it's supposed to look like Minkowski space, right? So in particular, the areas of the spheres here should be going to infinity. That seems reasonable, right? Another one, it should be the case that R times the scalar field, that this, let's say here, this should have a limit as v goes to infinity, right? I mean, again, if you haven't studied wave equations very much, maybe that looks a little random, but this is a very sort of wave equations on asymptotically flat spacetimes at infinity will have their sort of leading order fall off should be, well, once they evolve for enough time, they should have the leading order fall off like 1 over r. So, I mean, you expect you can see this from the explicit solution formula, for example, in Minkowski space. It's natural to multiply by r, then this thing should have a limit. This limit is what's called the radiation field. And it in fact includes, say on Minkowski space, includes all the information about the solution. So this should be true. Again, you can see how these things are weak, because you could imagine that you want sort of maybe you want some higher order. It's not just that this has a limit, you want it to have some expansion or something. So we're working with very weak things here. And then there's also, this should also have a limit. We would want the Hawking mass, right? This should also have a limit as v goes to infinity. All right, so I'm just going to work with these requirements. Then I'm going to say that if these are true, it's asymptotically flat, even though in reality, you probably want to prove more, but okay. Right, and this limit, this thing that you get when you take the Hawking mass and you go all the way out to null infinity, this is the so-called Bondi mass. Right, as opposed to if you take a space-like hypersurface and you go, if it's asymptotically flat space-like hypersurface, you go to infinity, you get what's called the ADM mass. All right, and these are things that these are important conserved quantities associated to asymptotically flat spacetime, so they should be defined here if our thing is actually asymptotically flat. Um, you could say that, but it will be here already. I mean, it should be non-negative, but that's a theorem. You don't need to assume that. Like it will be. I mean, if you have complete initial data, that's like, I mean, in this context, so in spherical symmetry, it's sort of even sillier because you can kind of solve sideways. But so if you have any spherically symmetric spacetime where, as long as you're always like, all your curves are coming out of the axis, and if it is indeed the case that M vanishes at the axis, then just by integrating the propagation equations for M from the axis, you will see that it's not negative. So our M has to be non-negative. We already know that. So it's a question of does it have a limit? Other questions? Great. Okay. So, well, unfortunately, this doesn't happen here. And it's sort of clear, right? Well, I guess I think one of them occurs, right? And but two don't. And it's sort of you can kind of see it just because of scaling.
Charge drop and two u equal to negative one, or just v.
Oh yeah, sorry, yeah, yes, because these are all statements about the data. Of course, my space-time, like weird stuff ends up. I mean, this is something weird. I just want to say that initially, I already argued that we have this, we're like C1 gamma kind of for the scalar field, and then I just want to say that also it's not like it's not funny in infinity. And here it's some requirements. Okay, so these don't hold. All right, so these fail. So these fail, for k positive. Which is this situation we're in. So some of it just by scaling, you can see that it's probably not reasonable. So why? Because if you are, so why? Well, I mean, first thing is sort of a heuristic. The first thing you can do is you can check that it's sort of a miracle has to happen for it to work out. And why? This is just by scaling. So we know that, so phi, right, um, is equal to some function of v over minus u plus, right, k log, or maybe it was minus k, right? Get the is looks like this, right? Um, right, again, so we're going to set u equals -1 and look at v very large. Um, well, I guess it could be the case that goes. Yeah, I mean, it could be the case that this goes to 0, but it's not sort of forced by the sort of by scaling, it's not sort of forced. In other words, it's, so phi has, because it has the scaling degree 1, so you would need to be the case that phi bar, so I guess this, when say u equals -1 is just going to be is going to be 0. So you would need that phi of z, converges to 0 as z goes to infinity. All right, I guess that could happen, but it's just that just by scaling, it's not like, so you could have gotten lucky that sort of the quantity, oh sorry, well, yeah, this is what I mean. Because, all right, because we need that, right? We're gonna then multiply by r, and that needs to have a limit. So I need, in order for that to possibly be true, I would need this to go to infinity, and moreover, sorry, wait, to 0. And moreover, I would need it to have the correct decay in z so that, when I multiply by r, I get a limit. And there's no sort of, by scaling, there's no reason. And similarly, remember that so 2m over r, which is equal to mu, this is actually just a function also of v over minus u. So again, by scaling, the natural scaling is that m behaves like r, not that it is finite. So sort of just by natural scaling, it would diverge. Um, and you know, and indeed that's what happens in these. You can check. So from whatever one of these propositions where you have all of this, all this explicit information as s goes to infinity, you can check that, you do indeed have that this. So in reality, this goes to infinity, for example. Okay, so that doesn't work. However, it's actually not such a big deal. Why? Because you can implement what's called a truncation argument. And this is something that comes up in uh, other PDEs, similar kind of considerations of here. All right, so we can resolve this. All right, so we can resolve this with a called a truncation argument. Truncation. All right, so let me draw the picture for what I mean. Well, I'm not really going to. Again, I'm just going to indicate what the steps of the proof would be. I'm not going to do them. Some of it involves something that we're going to still we'll sort of discuss later. All right, so here's u equals 0. Here's v equals 0. And here's our u equals -1. So here we have this picture, right? So the idea of the truncation is you do the following. So you draw, well, first of all, I'm free, I can take, well, I'm going to now relate, instead of calling this u equals -1, I'm free to work with, say, u equals minus, say, delta, for some delta very small. Right? This will be useful to get some smallness in a construction later. And now what I want to do is, okay, and then I'm going to consider I'll draw some curve here. This can be just v equals 1. All right, the portion of v equals 1. So here's v equals 0, v is negative here, here's v equals 1 here. And then what I'm going to do is I'm going to construct a new solution by solving what's called a characteristic initial value problem, which is one of the things that we are going to discuss that we haven't discussed yet. All right, so let me tell you how that works for the Einstein scalar field system. So what is this? All right, well, it says the following. So the normal initial value problem for the wave equation, like what I discussed in the, well, I guess before the winter school, is the Cauchy problem, right? You start with, like for the, you have a space-like hypersurface. You would input, like if you're solving a wave equation, right, that's like you put the solution and its time derivative and then you solve, right? For the space-time, you do, Riemannian manifold in a second fundamental form. And then this Riemannian manifold ends up being a space-like hypersurface. But you can also put data on things that will end up being null hypersurfaces. This corresponds to solving a characteristic initial value problem. So what you can do is, this is a general fact, so you can have some things like this. So you can call this, some u equals constant. I mean, what you can always, without loss of generality, call it u equals -1. I'm just talking, this is now the general form of this, not have to do with our solution. And you can call this one, you can always call it v equals 1. And then what I want to do is I want to put data, here and data here. And then I want to claim I can for at least a short amount of time, I can always get a solution inside here, right? That's like how, local existence works, right? It's a nonlinear equation, things could blow up, but all right, now I have to tell you what's the right data to put in this context. So it turns out that the right data you can put is you can pose basically the R, this, and this sort of, well, along both hypersurfaces. So along v equals 1 and u equals -1. I should say, well, let's assume that R, so we want R at this point. Let's consider the simpler case where this is greater than 0. Right? So again, if you're thinking in regular space, you have these cones, think about light cones, and you can have two cones. The like generic setting is that when they intersect, there's a sphere, right? So a cone is a three-dimensional object. And so you should intersect the two-dimensional objects. So that corresponds to like R, where they intersect, this not being 0. You can also have the case, of course, like, I mean, you could try to solve, you could have a single cone coming from a tip, like from, and then you could try to put data on that and solve that. That's also somewhat reasonable, but that's a much more subtle problem because now your bottom has higher codimension. It's like the not generic case. So let's consider this case. This is I'm going to do it up here, and that's what's relevant. Here, this sphere, I'm not hitting this place where R equals 0. All right, so then what you can do is you just pose these along them, and all you have to do is make sure that what I called before the null constraints were satisfied. So you just have to make sure your data is consistent with Raichaduri. Right? These are these equations that involve like the second derivative of the R function with respect to u and v. So once you've posed all of these quantities, then the Ricciardouri equation is something which you could ask, is it true along here? The point is it only involves like so along, say, u equals constant, it will only involve, you look at the v derivatives of r, that one that has v derivatives of r will only involve v derivatives of phi and involve r and the lapse. So I mean, it's not reasonable to try to make a solution if your data is already not consistent with it. So you have to solve that. But then and then you have the same one in the other direction. But then if you solve those, you're good. Okay. It's similar to how for the space-like problem, they're constraint equations. What's nice is that for characteristic initial data, we'll talk about this for the vacuum equations later. I mean, somehow because the constraint equations are Ricciardouri is sort of is a lot easier to understand because it's sort of just a transport equation compared to the other constraint equations are more complicated. Okay, so as long as you satisfy your Ricciardouri, you can always solve a bit. And then it's the usual thing, like in PDEs, that not only can you solve a bit, but you can keep solving. You have like blow up criteria, meaning you can keep solving as long if nothing like blew up. If weird stuff doesn't happen, like as long as r doesn't go to zero, as long as you can prove that r hasn't gone to zero in some region and the lapse hasn't gone to zero or gone to infinity, then you can always solve a little more, right? It's the usual thing. Like for ODEs, you can keep solving unless your quantity actually goes to infinity. All right, so in the last 8 minutes, what's the relevance? Well, what we're going to do is put we're going to try to solve such a thing here. And so here's let me just redraw the picture. All right, so what I'm going to, yeah, so it's like I'm going to start with some hypersurface way up here, u equals minus delta. There's not any reason that I have to take u equals minus one, right? I can recall my coordinate, whatever. But I'm just going to, in the coordinates where I constructed the solution, I'm going to actually take u equals minus delta. And then I could just kind of forget about this stuff. I'm going to do that. I'm doing that so that I gain, because then this region will be size delta. That gives me some smallness that will be useful. All right, and then, right, then we have this u equals 0. Right, then I said I draw this, v equals 1. All right, and then what I'm going to do is, so along v equals 1, I just put the whatever data, I put the sort of induced data from the solution. Right, because I want, I mean, yeah, here's my original, so here I'm going to put my original solution. And I'm going to need it to be, so over here, I want everything to be smooth up to there. So I'm just going to put whatever the limits of r, omega, and phi are there. And then what I'm going to do is along u equals this, I'm going to just glue. So, all right, so let's say, so for, v, say between 1 and 2, I'll just put I'll put whatever data was there before. I'm going to put whatever was there before. And then for here, I'm going to put I want to put data. I'm going to put a trivial scalar field. All right. And then I'm just going to sort of interpolate. Then in between, I'm just going to interpolate between these. So I want to interpolate, and then for v between 2 and 3, I'm just going to, so I put some, here's 1, here's 2, here's 3. So here I want phi, say, to be 0. Here I have whatever, just came from the space-time. Because, for example, I want this point to be rigged. I want everything to match up at that point. So I go a little bit in, I just put whatever was there before. And then now I want to make it match up. So I just put something. And of course, there's something to check here. You have to check that I'm going to interpolate in a way that's consistent, in a way that's consistent with Raichuduri. But you can do that. Okay. Basically, again, I mean, Raichuduri is just one ODE for, say, the R function. So once you've uh once you can put, say, phi equals 0, you can even put the lapse to be 1. Then you can just solve this ODE to tell you what R is. And then you just have to make sure that then because the initial data will all be determined already from here. It's a second order ODE for R, so you just will solve from here. You have to solve Raichuduri, so it is what it is. And then you just have to hope that it, you know, looks reasonable, but it will sort of look reasonable. I mean, it's not so um, complicated here because it's just an ODE. So, if the scalar field is 0 and the lapse is 1, then Raichuduri is just becoming that dr, the second derivative is 0. So R will just be, A times V plus some constant. So basically, up to some rescale of your V, R will be exactly like the normal R function. Okay. Yeah, anyway, so you do that. And then you want to argue that, so this region, call this region, I don't know, A. So you do that and you check that, and then check that, because you put the scalar field to be 0 and say the lapse to be 1, check that you are asymptotically flat. There's a lot more things you can do, but we're just trying to construct, something. All right, so you can check that now this thing will be fine. But now, of course, because you changed the thing here, now this part of the solution, you no longer know what happens there. And we need to make sure you could mess things up because now it could be the case that you solve a bit and there's a black hole or something. This is the whole point. We want it there to be no black hole. We want it to be asymptotically flat, and we need to check that null infinity is incomplete, right? So ideally, what will happen is that over here it just looks like flat space, and then again we just have this null hypersurface here, and then this distance. Remember, this is the incompleteness of null infinity, is that the ingoing rays always hit this in finite time uniformly as you go out. That's the finite singularity, and that should happen no matter how far you go out. All right, but we don't know. Right now we don't know what's going on here. And here I won't really give the details, but it turns out that you can, because the solution, one way to think about it is the regularity of the solution here, the derivative of the scalar field is Holder continuous. So you're in the BV norm. You're better than BV. So remember, along V equal 1, you're better than BV. And somehow, and if you think that various, you do wave equations and things, you have various the natural norms will involve integrations, in the various variables. And so because I chose this delta to be small, the size of this integral, the size of everything here, if I take delta small enough, sort of all the relevant norms that come up, and this is something we'll talk in much more detail later, and in fact in the context of the vacuum equations, but just trust me for now. The relevant norms that come up here are integrals in this direction, but because of this smallness, and because I have enough, I'm actually better than BV. Sort of the relevant norms for sort of controlling that you try to control it to understand the solution up here, they start small here. You have some smallness here, right? And then, here's sort of some finite region. Then here things sort of become trivial. They're just like Minkowski space. And so because of that, you can invoke those things to argue that, nothing actually can go wrong up to there. It's almost like, all right, if I stopped here in finite time, this would really be just from local theory. If this was finite, then it's just saying if I just put delta distance here and I'm in something, I have enough regularity I'm sort of better than my Wilposinus, and that I can always get existence up to there. Nothing can go wrong. It's like saying it's sort of some small data. If data is small enough, I can always go, time 1. All right, so then you have to do some more work to show that, I can make this thing go all the way out and have with this data and sort of propagate up, but that's something you can do. And again, Jay Deep's that appendix to Jay Deep's paper, he writes out a full proof of this if you're curious. Okay, so it's 5. All right, well, let me quickly end. All right, and so you do that, and then finally at the end, having constructed it, and then finally at the end, you can indeed check. You can check that future null infinity is incomplete. Right. So in other words, what that means, you can start, I mean, again, it's spherical symmetry. So it's, I mean, you know the incoming geodesics, you don't have to solve for them. You know that this is the direction of the, you know, they're all just these various v equals constants. And then all you have to do is you have to compute, using the metric, what the like the length, the affine, what's the actual length of this of if you solve for the geodesic equation in these directions with parallel transported, just again, because everything's becoming flat out here, the eventually everything, your initial vector is reasonable to just take d by du. That's sort of more or less parallel transport it. And then you check that you solve the ingoing geodesic with that derivative. Well, again, because everything's in reality becoming very close to flat space there, that it's just gonna be what you think. It's just gonna be, u going constant, and you can check that in time one, you always hit u equals 0. Right. Um, Again, all of that is explained in J. Deep's appendix. And that's the last thing I'll say. Sorry for going over slightly. Is that now, in some sense, the rest of the course is the motivation for the rest of the course is try to understand if we can find similar phenomena, similar type of solution, similar phenomena for the Einstein vacuum equations. So, and we're going to, of necessity, we cannot work in spherical symmetry for the vacuum equations. And that introduces an immense amount of technical complication. And the eventual punchline is some aspects of all these things we can do, and some things would be interesting to do, varying levels of difficulty. And so we'll see where we get. All right. So, okay. So I'll see you on Wednesday. Sorry for going over.